be about fusion, fusion of LiDAR and camera. And the presenter will be Haolin Zhang. Haolin is a master's student at the Ohio State University. He's from our group. And Haolin, you can begin whenever you are ready. We cannot hear you, Haolin. Can you please unmute?
Okay, so can you say
yes, we can hear you, yeah.
Okay, hi everyone, I'm Haolin Zhang, and today I will present our work using vision and point cloud for faraway pedestrian detection. And in urban scenarios, it is important for autonomous vehicles to interact with pedestrians. Our research also focus on the pedestrian perception tasks, including 3D object detection, especially for pedestrians, and the pedestrian intention estimation. So for faraway pedestrians, detecting them is difficult. So our goal is to detect and localize them as accurately as possible. For nearby pedestrians, detecting them is not a big problem. So we still hope to be able to predict their intention in advance to assist the control systems. And today I will mainly talk about our faraway pedestrian detection work. And at the end of this presentation, I will also talk about our ongoing project, pedestrian intention estimation. First, I will give you a brief introduction of 3D object detection. The problem we tend to solve is that given the input sensor data, our algorithm should output the classification and the localization for all objects as shown in this figure 1. And to achieve this task, we need first collect the input data from many kinds of sensors. In our work, we mainly focus on camera and LiDAR. And by using camera and LiDAR, the existing 3D object detection methods are mainly point cloud only based or the point cloud RGB based. They are all good for most objects, but not good for faraway objects. And I will discuss them later. Before we go into the details of our work, I will give you an interesting example to show this interesting example. First, let's see the original point cloud here, and then I will zoom in the part of this point cloud and see, can you identify or classify any object in this small area? It's hard, right? And even if I tell you there is an object inside of this small area, can you identify it? It's still difficult because you cannot find exact shape for any object. Let's see the same frame in the image domain. Let's see this picture. You can easily find this faraway pedestrian and these cars in the picture. Now I will tell you this small part of point cloud belongs to this pedestrian. See, this is the problem of faraway pedestrian detection. However, current methods are mainly based on deep neural networks and trying to learn the point cloud shape of the object. It will be workable for close nearby pedestrians. The shape is clear, but when the distance is greater than, for example, 60 meters, even humans cannot find the exact shape of this faraway pedestrian based on only maybe 2-point scan. Such faraway objects is really difficult for existing methods to detect them, but we cannot overlook it since this faraway distance is not very far for a fast-moving vehicle. For example, a fast-moving vehicle, can traverse 60 meters on only 2 seconds by moving at, for example, moving at 70 miles per hour. So it is still important to detect such faraway objects. And However, the sparsity problem in the point cloud does not exist in 2D image. For example, this faraway pedestrian in the image, it still contains 400 pixels in the picture. It can be easily detected by a 2D detector. So we think a frustum-based method can be a good candidate to solve this problem, to solve the faraway pedestrian detection problem, since such methods use 2D detection to assist 3D localization. But we cannot directly use current frustum-based method because they still use point cloud representations to find the object shape to localize them. Our idea is we use the 2D detection to assist 3D localization following the frustum-based method, but in 3D, we do not try to find the exact shape of the object. We use the point cloud itself to find the object centroid, the position of the pedestrian. Thus, we propose our method, faraway frustum, to detect faraway objects, including pedestrians. And there are 3 main stages in our method. First, frustum generation. Second, centroid estimation. And the last, box regression. And I will illustrate them one by one. At the first stage, frustum generation, first we do the 2D instant segmentation to the image, and we detect the objects and find the segment the objects in the 2D image. And then based on the 2D results, we use the 2D bounding box or the 2D semantic mask to do the 2D to 3D reprojection and find the 3D box frustum or the 3D mask frustum for every object. After that, at the second stage, we collect the point cloud inside of the frustum, and we use a clustering method to estimate the 3D centroid of the object I. We analyze the pedestrian distribution in KITTI dataset, and first we draw a line here to indicate the pedestrian have 10 LiDAR points scanned, and we set a faraway threshold, for example, 60 meters, such that most objects with a distance greater than 60 meters have less than 10 LiDAR points. So to determine whether the object should be considered as a faraway object, we compared our estimated distance with our object threshold, this threshold, and if the distance is greater than the threshold, we consider this object is a faraway object in our method, otherwise not. At the last stage, we do the box regression. If it is a faraway object, we use our faraway frustum network to refine the depth, the distance of the pedestrian, and based on the refined centroid, we do the box regression to find the bounding box for the object. And if it is not a faraway object, we directly use a state-of-art method to detect this objects based on learned point cloud representations. So why can our method be better for detecting faraway object? I will illustrate in detail again. Let's see this picture. The existing state-of-art method try to find the exact shape of the pedestrian. But for a faraway pedestrian or faraway object with very sparse LiDAR, for example, 3 points, the existing method, the learning-based method, cannot find the shape of this object. While our method used a cluster method for this point cloud to find the estimated centroid of the object, then we use a simple neural networks to refine this distance to find a more accurate position of the faraway object, and then regress the box. So it will be easier to achieve this task. Finally, we did some experiments on KITTI dataset. Let's see some qualitative results. First, in this scenario, only our method can detect this faraway pedestrian in both 2D and 3D. However, for frustum point nets, it is also a good frustum-based method similar to ours. But since it relies on point cloud representations to find the shape of the pedestrian to localize them, it may mistakenly recognize the shape of the pole as the shape of the pedestrian. And for PVRC, since it is totally based on point cloud representation, so it cannot even find any object in such a very sparse point cloud. We also test for car, and the result is similar. Only our method can detect such a faraway car, while other methods cannot. There are some quantitative results. First, let's see the average IOU comparison. Our methods outperforms other state of methods for detecting faraway pedestrians and faraway cars with a higher average IOU. And none of the methods, except for ours, can achieve an average IOU of 0.1. And for mean average precision comparison, let's focus on the pedestrian over 16 meters here. And our methods outperform other state-of-art methods with a big margin. And we also test for car over 75 meters, and our method outperform other state-of-art methods with a big margin. Again, these are our conclusions. First, our method works better in detecting and localizing faraway objects because we take the advantages of dense image data to find the faraway object first, and then we circumvent the disadvantages of directly using the sparse point cloud representations to localize them. And our detector is also flexible because it can be easily combined with a state-of-art method to build the overall detection system. And if you are interested in our work, you can find more details in our paper here. And then I will talk about our ongoing project, pedestrian intention estimation. So for nearby pedestrians, detecting them is not a big challenge. You can use a state-of-art method to detect them accurately. So higher level tasks are more important. For example, pedestrian intention estimation. And our focus is to predict whether the pedestrian close to the street will cross the street. And existing method based on computer vision is good, but not good enough for many cases. We find a big problem inside of this existing methods. That is, existing methods do not fully utilize pedestrian factors and the contextual factors. Recent research shows that pedestrian intention is highly linked to the contextual factors and the pedestrian factors. The basic idea of existing computer vision based method to do this task is to use convolutional neural networks to extract the features from the cropped pedestrian images. And based on a RN model, they use these features to do this prediction task. And I will show you some problems faced by such methods. Let's say the top example here. The pedestrian, let's focus on the pedestrian inside of this blue box. The model will predict this pedestrian as a crossing pedestrian. But the real intention of this pedestrian should be not crossing. So if for a human driver, it is easy to predict that this pedestrian will not cross the street. Why? Because there is a green traffic light here. So that's why the contextual factors are very important in this task. And for more special cases, current model cannot find more useful features from the image itself for these special cases. So that's why the pedestrian factors are also important in this task. This is our idea of achieving this task. We try to improve the current method by utilizing the pedestrian factors and the contextual factors. And the detail is still being considered since this project has just started and is in progress. And we expect our math based on the contextual factors and the pedestrian factors will be better for more special cases. That's the whole content of my today's presentation. Thanks for listening, and you can feel free to ask some questions.
Thank you, Haolin. We have 3 minutes. Do we have any questions? Let me ask one question, Haolin. So when you mention faraway pedestrians and when you mention it's around 60 meters, what is the benefit of having a high performance in this region? And what is the main problem here of the state of the art?
Yeah, I will illustrate it again. Since for these faraway pedestrians, you may think it is far away. We can detect it in close distance, but if it is for a fast-moving vehicle, it still be important because for a fast-moving vehicle, it can traverse such a faraway distance under maybe 1 to 2 seconds. So it's still useful for us to aware of these faraway pedestrians. Even we cannot exact find the shape of the pedestrian or detect this pedestrian with higher IOU. But if we can detect it in advance, it will be helpful for autonomous vehicles.
In other words, 60 meters is not actually very far away for a fast-moving vehicle, and the state of the art completely fails around 60 meters, but it shouldn't. I guess that is one of the main points of this research. So thank you for the clear presentation. Do we have any other questions? Thank you, Haolin. It was a great presentation. Thank you very much.
Thanks everyone.
Our